Let's do a simple, dangerous thought. Imagine you have a button that sends a single bit of information, just yes or no. No picture, no video, no sci-fi warp bubble, just a clean, controllable signal. And it travels faster than light. Not a little faster, not almost faster, period. Now ask the question everyone avoids. What would that actually break? Not Einstein said you can't, not it violates relativity. I mean, what mechanism stops it? What physical rule would the universe be enforcing? Because the speed of light is about 300,000 kilometers per second. That's a number you've heard so many times it sounds like trivia. But here's the part everyone misses. If you can send information faster than light, you're not just being fast. You're messing with the wiring of cause and effect. You're messing with before and after. And that sounds dramatic until you realize this. In everyday life, before feels absolute. You drop a cup, then it hits the floor. You ask a question, then you hear an answer. But physics doesn't promise you an absolute then. It promises you something subtler, a structure that decides what can influence what. So the real question isn't, why can't anything go faster than light? The real question is, why does the universe have a causal speed limit at all? Why is there a boundary between events that can be connected and events that can't? I have a habit here. I don't accept labels. I ask what the label is doing. So let's do it my way. No authority, no slogans. Just, what's the rule? And why is it unavoidable? Most explanations stop at the headline. Nothing with mass can reach light speed. Light speed is the cosmic limit. Relativity says so. Okay, but that's not a mechanism. That's a verdict. It's like telling someone, you can't move your rook like that. Chess says so. That doesn't teach you why the rule exists. It teaches you how to obey it. And physics is not a list of commandments. Physics is the set of constraints that keeps reality consistent. So here's the promise of this video. By the end, you'll see that the speed of light limit isn't about light being special. It's about causality being special. You'll see a clean geometric picture, the simplest one in all of modern physics, that draws a boundary around every event in your life, what it can affect and what can affect it. You'll also see why faster-than-light messaging is not just a speed upgrade. It can become a time machine for contradictions if you're not careful about what you're assuming. And crucially, we'll separate the real thing from the imposters. Because physics is full of things that look faster than light. Patterns, shadows, sweeping beams, weird wave behaviors. So we'll ask the sharp question, what counts as a signal? What counts as information? What counts as cause? Then we'll finish with 3 modern checks that don't care about your intuition. First, GPS has to correct relativity or it drifts. Second, muons from cosmic rays shouldn't reach the ground, but they do. Third, particle accelerators push objects insanely close to light speed, and the math predicts exactly what happens. No slogans, just structure. Now we need one everyday anchor before we go abstract, because the weirdest ideas always start with something boring. Think about the most normal delay you experience. You send a message. Are you there? And for a moment, nothing. That tiny pause is not psychological, it's physical. Even across a city, information takes time to travel. Across an ocean, more time. To a satellite and back, you feel it instantly. Now here's the trap. In daily life, we treat time like it's universal, like there's one master clock in the sky, ticking the same for everyone. But how would you prove that? How do you even define 2 things happened at the same time when those 2 things are in different places? You need a method, a protocol. You could try synchronized watches, but then you have to synchronize them somehow. And somehow means sending a signal, a flash of light, a radio ping, anything. And the moment you admit that, you've smuggled in a constraint. Your definition of same time depends on how fast your signal travels. So suddenly this isn't philosophical at all. If there were an instant signal, you could define simultaneity easily. Push a button, everyone updates immediately, done. But if the fastest signals have a finite speed, then now is not a global sheet spread across the universe. Now becomes something local, something constructed. So when someone says faster than light, don't imagine a spaceship going zoom. Imagine a new kind of synchronization, a new kind of ordering, a new kind of before and after. And once you touch that, you're touching the core of relativity. Okay, ready for the first real AHR? We're going to draw the rule, not with equations, with a picture you can't unsee. Here's the experiment. Make it visual. Picture empty space, no planets, no air, just you floating with a perfect flashbulb. At one instant, call it event E, you fire the flash. What happens next? The light expands outward as a growing sphere. Every second, that sphere gets bigger by about 300,000 kilometers in radius. Now freeze the scene and ask, which parts of the universe can know that E happened? Not eventually, not in principle, at a given moment. At 1 second later, only points inside that 300,000 kilometer sphere can be affected. At 2 seconds, a bigger sphere. At 10 seconds, bigger again. So E doesn't influence everything. It influences a region that grows at a specific rate. That's already the speed limit, hiding in plain sight. Now do one more step, the part that turns this into geometry. Instead of drawing space as a line and time as a separate feeling, imagine a simple graph. First, up is time. Later means higher. Second, sideways is space. Farther means more to the side. Your flash happens at one point on that graph. As time moves upward, the expanding light sphere traces out a boundary. In this picture, it becomes a cone. Everything inside that cone is reachable by signals moving at or below light speed. Everything outside is not. And that's the punchline. The universe is not telling you, don't be fast. It's telling you, causes live inside cones. If an event is outside your cone, it's elsewhere in a deeper sense, not just far away, but causally disconnected from you unless you wait. And if you try to send a controllable message outside that cone, you're trying to draw a causal arrow where the geometry says none should exist. Next, we ask the harder question. Why do different observers, moving relative to each other, still agree on the shape of these cones? Because that's where the limit stops being about light and becomes the structure of space and time themselves. So far, this cone picture feels like it's about light, flashbulb to expanding sphere to cone boundary. But here's the deeper move. The cone is not because light is fast. Light is fast because the cone exists. That sounds backwards, so let's earn it. In the 1800s, Maxwell writes down equations for electricity and magnetism, and those equations spit out a wave, an electromagnetic wave, with a definite speed set by electric and magnetic constants, not infinite, not whatever the source feels like, a fixed number. Now, if you were living in the old mindset, you'd say, okay, fixed speed relative to what? Because in normal life, speeds depend on the observer. A car is faster than you if you're standing still, slower if you're chasing it. So people assume there must be a medium, an ether, that defines the true rest frame for light. Then comes the shock. Experiments like Michelson-Morley don't reveal that ether wind the way you'd expect if light had a preferred frame. So Einstein makes a brutal simplification. 1, the laws of physics should look the same in every inertial frame. 2, the speed that Maxwell's equations predict is the same for everyone. If you accept those two, you don't get a weird rule about light. You get a new geometry. Minkowski later says it cleanly. Space and time are not separate arenas. They're one structure. And C is the conversion factor between them. Like how degrees convert arc length on a circle, or how exchange rates convert currencies. That's why C shows up everywhere, not only in light, but in the maximum speed of causal influence. The cone isn't a property of a flashlight, it's a property of space-time. And once you see that, the next step becomes inevitable. If you try to push something closer and closer to the cone boundary, what exactly happens to energy and motion? Take something with mass, anything, an electron, a proton, a spaceship. You accelerate it. At low speeds, it's simple. Push harder, it speeds up. Double the force for the same time, roughly double the change in speed. That's your daily intuition. But the closer you get to light speed, the less that intuition applies. Because what's really growing isn't some mythical relativistic mass. What grows is the factor that links energy, momentum, and velocity. Here's the practical version. First, at 0.5 c, it's already noticeably relativistic but manageable. Second, at 0.9 c, you've entered the "this is expensive" regime. Third, at 0.99 cents, you can dump a ridiculous amount of extra energy in, and the speed barely budges. It starts to feel like you're approaching a wall you can't reach, not because the universe is resisting like air drag, because the geometry is telling you you're trying to rotate your trajectory closer and closer to the light-like direction, and that costs unbounded energy. Now watch how this shows up in the real world. 1. Particle accelerators. They don't break relativity, they confirm it. Particles get insanely close to c, but what increases dramatically is their energy and momentum, not their speed crossing c. 2. Cosmic ray muons. Muons are unstable. In the lab, they don't live long. So if you create them high in the atmosphere, your naive expectation is they should decay before reaching the ground. But many reach the surface anyway. The clean explanation is relativity. In our frame, their internal clock runs slower when they're moving near C. Equivalently, in their frame, the atmosphere is length contracted. Different language, same geometry. So C isn't just light speed, it's the slope of the boundary that connects time, distance, and causality. Okay, now let's trigger the confusion on purpose, because there are things that look like they go faster than C, and if you don't separate them correctly, you'll think physics is lying. Here's where people get smug. They say, but we've seen faster than light effects, and they're not completely wrong. They're just mixing categories. Example 1. Take a laser pointer and sweep it across the moon. The spot moves. If you sweep fast enough, the spot can move across the lunar surface faster than light. So, did you just beat relativity with a cheap laser? No, because that spot isn't a single object traveling from one point to another. It's a pattern, a sequence of different photons hitting different places. No photon traveled along the moon faster than C. You just changed where the beam points, and the intersection point jumps. Example 2, waves in materials. In some setups, the phase velocity of a wave can exceed c. Even the group velocity can do weird things in dispersive media. But the part that matters for information is not how fast the crests seem to slide. It's whether you can send a controllable new bit that arrives earlier than any light speed influence. Example 3, quantum entanglement. Correlations appear instantly across distance. At least they don't look like they're mediated by a slow signal. But you can't use entanglement alone to send a message faster than light because you can't choose the outcome you get. So you're left with this tension. First, patterns can look superluminal. Second, some wave descriptions can look superluminal. Third, some correlations feel superluminal. And yet the hard claim remains: no causal signal. So what's the clean criterion? What exactly counts as information traveling in physics? That's where the cone becomes a filter. Here's the rule that slices through the noise. The light speed limit is a limit on causal influence, on controllable information. Not on every number you can compute and call a velocity. You can make a shadow sweep across a wall faster than c. You can make a wave's phase do something that looks faster than c. You can even construct situations where a peak of a pulse seems to emerge early. But none of that automatically gives you what you really want, a yes/no that you can choose, send, and have someone receive sooner than any light speed signal could allow. Think about what a message requires. A message isn't just an event. It's an event with contingency. You could have sent the opposite. That contingency has to physically propagate. And in relativistic physics, the propagation of that kind of influence is tied to the cone. If an effect is outside the future light cone of a cause, then there exists some inertial frame where that effect happens before the cause. That's not a vibe, that's geometry. So when physicists say no faster than light, the sharp meaning is you cannot send a causal influence outside the cone, because doing so breaks the consistent ordering of cause and effect across frames. And that's why the superluminal-looking cases survive. First, the moonspot doesn't carry a single causal chain from point A to point B along the surface. Second, phase velocity isn't the speed at which new information is created at the receiver. Third, entanglement correlations don't let you control what the distant observer sees without a classical channel. So the world is not contradicting itself. It's enforcing a specific definition of what counts as causal. Now, if you want the heart of the title, faster than light, here's the part everyone misses. It lives in the next step. Because once you allow one controllable FTL message, you can start building something that looks like the universe talking to itself in reverse. That's the paradox we have to face. Now we hit the part that sounds like a trick, until you realize it's a straight consequence of the cone picture. Assume one thing, just one. You can send a controllable faster-than-light message, a yes/no you choose. And the laws of physics still respect the usual relativity principle. Different inertial observers are equally valid. Okay, build the simplest setup. Alice and Bob are moving relative to each other, nothing exotic, just two ships passing in deep space. At the moment they pass, they synchronize a plan. Later, Alice will send Bob a single-bit FTL message. From Alice's point of view, she sends it at time t sub A. It reaches Bob at time t sub B. Fast. Great. But here's the geometric knife. If the message path is outside the light cone, space-like, then there exist frames where the time order flips, meaning in Bob's frame, it's possible that the receive event happens before the send event. Not because anyone is cheating, because for space-like separated events, before and after is not absolute. Now you might say, so what? It arrives earlier in Bob's coordinates. Who cares? Here's why you care. Give Bob the same FTL ability and let him reply instantly the moment he receives Alice's message. Because of the flipped ordering, that reply can be arranged purely by relative motion and geometry to arrive back at Alice before she sent the original. Now you've built a communication loop that can carry information into the sender's past. And that's not time travel with a spaceship. That's a contradiction machine. Alice receives a message that says, don't send. So she doesn't send. So Bob never receives. So he never replies. So Alice never receives. The point isn't the drama. The point is, the cone prevents these loops. FTL as signal tries to punch a hole through the cone, and the geometry punishes you with causal knots. So what's the real resolution? It's not light is special. It's not Einstein forbids fun. It's this. Space-time has a built-in causal structure, and the speed c is the slope of the boundary that keeps cause and effect consistent for everyone. That's why the cone is the main character. Inside the cone, you can influence. You can be influenced. Cause makes sense. On the cone, signals at the limit. Outside the cone, you can label it elsewhere, but you cannot wire it into a controllable chain without risking causal loops. Historically, this wasn't invented as philosophy. It was forced. Maxwell's equations implied a fixed wave speed. Experiments didn't reveal a preferred rest frame for that speed. Einstein took the hint. The laws must keep the same form for all inertial observers. Minkowski made the punchline geometric. Space and time are one arena, and C stitches them together. Now, if this were just math elegance, you could ignore it. But you can't, because modern technology and modern measurements lean on it every day. 1. GPS. Satellites and receivers are moving relative to each other, and they sit in different gravitational potentials. If you treat time as universal, their clocks drift relative to Earth clocks. The system has to apply relativistic corrections, or positions wander badly. 2. Muons from cosmic rays. They're created high in the atmosphere, and many survive to the ground. That's not a motivational poster, it's measured. Relativistic time dilation, equivalently length contraction, is the clean explanation. 3. Particle accelerators. We pour energy into particles and push them extremely close to C. They don't cross it. Instead, their energy and momentum ramp up exactly the way relativistic dynamics predicts. So go back to the opening button. Just a yes/no faster than light. Here's the twist. That button isn't a speed upgrade. It's a demand that the universe let causes leak outside their cones. And once you do that, before stops being stable. That's why the limit feels so absolute. Not because nature hates shortcuts, but because nature protects consistency. My instinct has always been, don't worship the number. Ask what it does. And what C does, quietly, relentlessly, is draw the line between a universe that can tell a coherent story and a universe that can contradict itself.